Hello, this is concrete path, and let's take a problem related to combined stresses. After that, we have next topic, that is your springs. So the problem says you have a solid steel circular shaft, then it has to carry a torque of 40 kilonewton meter and a bending moment of 20 kilonewton meter. And you need to say what should be the diameter of that shaft. By using, you can use two theories of failure. You have to use that two theories of failure, and taking the factor of safety 2 and the value of E equals to 200 kilonewton per millimeter square. And the yield stress for this material is yield stress Fy 250 megapascal. Poisson ratio 0.3. Okay, so we can take two. You had to take two theories of failure for this one. So there is what we call as combined stress, because your torque is applied, bending moment is applied. So if I use the first method, that is maximum principal stress theory. So I would say that sigma 1 should be less than or equal to Fy by factor of safety. So major principal stress in multi-axial loading should be less than the that yield strength, or that major principal stress in the uniaxial loading. So how can you get the sigma 1 if you have a combined loading? So can we have the concept of equivalent bending moment? Equivalent bending moment. ME, do you know that value? ME equals to M plus M squared plus T squared. And from this, can I get the sigma 1? That is your sigma 1 would be in this fashion, 32 ME by pi d cube. That is your sigma 1. That's equals to, that should be less than or equal to Fy by factor of safety. So if I get the value of ME, then I can get the value of diameter. So if I use that, what should be the value of ME? I would say value of ME would be equals to 20 kilonewton meter plus root of 20 square plus 40 square. So you get a value of ME equals to 32.36 kilonewton meter. So let's use that value. So that means you write 32 into that is your 32.36 kilonewton meter Newton millimeter divided by pi d cube. That should be less than or equal to, your yield stress was 250 megapascal divided by factor of safety of 2. So you get the diameter as equals to, that should be greater than or equal to 138 point, let's say 179 millimeter. Now we have to take one more theory. Now. So if I have one more concept, that is your equivalent torque. That's M squared plus T squared. And from this I can get tau max. So if I use that tau max theory, maximum principal stress theory. So if I write that second theory of maximum principal stress theory. So let's write maximum principal stress theory. Maximum shear stress theory. I would say tau max in the multi-axial loading should be less than or equal to tau max in the uniaxial loading. This is multi-axial loading, this is uniaxial loading divided by factor of safety. So tau max in the multi-axial loading would be equals to 16 Te by pi d cube, and that should be less than or equal to Fy by 2 into factor of safety. And if I get the value of Te, I would say I can get the tau max for the multi-axial loading. 60T into your T value of, that's your 40 square plus 20 square, and divided by pi d cube, and that should be less than or equal to 250 megapascal, and divided by 2 into factor of safety 2. So this value is in kilonewton meter, and this one is in Newton per millimeter square. So accordingly, you can convert that, and you would get a value of diameter should be equals to 153.9 millimeter. That's more. So this value, maximum shear stress value, shear stress theory gives you conservative value for design. So it gives you more diameter. That diameter is 154, and in the first case the diameter was 138. So it underestimates that what you can say strength of that tactile material. So we can use that. We can use that one for the design. Now coming to our main topic of for this lecture, that's what you call as springs. That we call as springs. Let's call them as springs. Let's call them as springs. Okay, springs. Springs. So there's some spring. What do you mean by that spring? What's the use of that spring? What is the function? So we say that the function of spring is to distort, or we can say is to deflect or distort. Is to distort or deflect, not permanently, but for some time, for temporary basis. So it's to deflect or distort upon loading. Then once you now remove that load, what you call as unloading, so it comes back to original position. Back to original state. So on the unloading, it would absorb energy. That means it would absorb energy. Then after that, it would release that same energy when required, when that you needed that. If you want unloading that or unloading up that spring, so it will release that energy. And so there is no permanent distortion. There is no permanent distortion, or we can say deformation. Distortion would be because of tau, and deformation because of normal stresses. So we have two kinds of springs. We say we have one is your leaf springs. And next one is that what we call as helical springs. So for the leaf springs, we say you use them as shock absorbers. We also call them as leaf carriages. That spring carriages. So let's say the sketch of that looks like some sort of in this fashion, that you apply some load of W, and we have the plates attached here. We have the plates attached to this one. This is one plate. Next one is that one more plate, third plate, fourth plate, fifth plate, in this fashion. So of varying lengths, we have plates of varying lengths. So we have plates of varying length. And yeah, plates of varying length, but the thickness of that each plate, but the thickness, if we talk about that, we say the thickness and the width. Let's say the width is W here, and the thickness is T. Let's say width is B. So we say that B and T is constant for all those plates, all those leaves. We call them leaves. So this is constant. B and T is constant. Section modulus of each plate is constant, BT squared by 6. And then we say that they are bent. If we talk about that, we bend them to the same curvature. They are bent to the same curvature. All are bent to same curvature. So it is designed based on that. We say it looks like a beam of uniform strength. Beam of uniform strength. You can see them in your, if you have trucks, if you have those railway wagons, railway carriages, wagons. We can take trucks, trolleys, cars. So there we have this kind of spring. They are called as shock absorbers. The next one is that what we call as helical springs. So we have these sort of springs based on that that angle between those, based on that angle in the spring. So we say that there are two kinds of that spring. One is your open helical, and next one is that closed helical spring. So for our syllabus, we say we have that closed helical springs. For the open helical springs, we have one that what we call as helix angle. That's alpha. That's greater than 10 degrees, and in this case, alpha less than 10 degrees. So if we make that for the closed helical spring, I would say you have some spring in this fashion. So there's some pitch. We call that as pitch. There's some pitch between one turn. Between one turn, there's some pitch. For one turn of that coil, there's a pitch term is there. If we say that the one turn is perpendicular to the axis of that what we call as helical axis. So if this, we assume that this is assumption that one turn is perpendicular to the helical axis, then we say that we can make that in one plane. So one turn can be shown in one plane. We can show that one turn in one plane. So if we say there is a entire one turn of that helical spring, so we say up to this point we have to reach. So I would say this is your one turn. I can call that. So I would say, let's wait. So up to this point, we can say from this point to this point, this is your one turn. So this part is your one turn. So up to this point, we say you can represent that because your alpha is less than 10 degrees. You can show that in one plane. So that's your one plane. You represent that entire one turn in a straight line with a length of 2 pi. And there might be some mean radius, r. So I would say 2 pi r. So the entire length is shown in one line, in a one plane. This is from the assumption that if the alpha is less than 10 degrees, we can say one turn is perpendicular to that helical axis. So I would say let's take that entire turn in one plane, 2 pi r, and there would be some pitch p, and there is some alpha. Then we say then tan alpha equals to p by 2 pi r. So accordingly, your pitch of 2 pi r tan alpha. So then we say that based on this one, we say you apply some load. On this what you call as closed spring. You apply some load. When you apply some load, let's say then we kind of show this spring in this fashion. We show this spring then in this fashion. We show. So there might be some what we call as that helical axis, and we say you apply a load of that p. Let's say you apply a load of p upwards, and to show that in the top view, I would show that in the top view in this fashion. So there would be some diameter of that spring also. There would be some diameter of the spring also. Now you are applying load in upward direction. So this is downwards, downward load, and this one is upward load, upwards. So you apply the load of P upwards on let's say on the center. You apply the load of P on the center, and there is some diameter D. There's some diameter D. This is dia of what you call as dia of spring. Let's call it as D, small d. And there is some you are applying a load. I would say what is happening to this dia of that spring? What's happening to this spring? Somewhere you cut any section somewhere. I would say this load P is trying to that load is trying to have a rotation about that section in the clockwise direction. So it's trying to rotate that rotate about that section. It's trying to rotate about that same section in the clockwise direction. So it's trying to rotate about that same section in the clockwise direction. I would show that. So it's trying to rotate about that same section in the clockwise direction. That means if we cut the section, there would be some section here, there would be some section here, and we can show that continuous also from other side also. I would say there's some section of diameter small d. So diameter small d, there's some diameter small d, and on that there is some resistance developed because your load is trying to rotate that in the clockwise direction. So there will be anti-clockwise resistance. So that would be some moment. I would call as let's call that moment as torque. So because this is because it's I would say there might be some long axis of that what you call as spring. So the load is rotated. The rotation about rotation is about that long axis. So what we call as, so the moment developed here is equals to torque. Torque equals to some P load into some radius of r. So we say that there is some radius of r. Then we approximate that the thickness is very less. So we say let's take that value of r as that of capital R. So there is some r. You multiply that also. So finally we say there is some diameter, mean diameter of the coil. This is mean diameter of the coil, dm. This is, we approximate at mean diameter of that coil. That's almost equals to 2r. So finally we say torque T equals to P times R. So your closed coil, when you talk about closed coil, we say it's subjected to what you call as torsional moment. Because of that torsional moment, we have torsional shear stresses, and we say that bending stresses and direct shear stresses are negligible. Bending sigma and direct shear stress are negligible. We say negligible. So this one is that dominant value of tau t. So if you talk about direct shear stress value, can you get the value of direct shear stress? So I would say you're applying load of P upwards. So resistance would be from the section of that spring D. So there, if you're applying load from the top, so there will be resistance downwards on each point of that section. Everywhere we have downwards that resistance, shear force developed. Anywhere that would be downwards. You cut any section, there would be shear force downwards. And if anywhere you cut the section, so there would be a shear force downwards. So if I represent that, if I represent this torque, if I have this diameter now, if I talk about this diameter now, so I would say this is your diameter D. There is some diameter D. So we have the diameter D, and your resisting torque is anti-clockwise resisting torque. So this is your TR, and we know that tau t is in the direction of TR, that is tangential. So here it would be tau t, here that would be tau t, that is equal to tau t, and in this one we have upwards tau t. But if you take that because of direct shear stresses, the direction would be always downwards. So direct shear stress will be always downwards. Tau t, tau d, here also tau d, and here we can say there is 0 on the top. Neutral axis is there. and tau d is 0 at the top and bottom, but for the tau t it's same on the surface. It is same on the surface. It's a function of r. Then we say that on one side, on one of the sides you have tau max, and one of the sides you have tau minimum. So if we talk about tau max and tau minimum, can we get the values of tau t and tau d? I would say tau t is equals to 16t by pi d cube, and if you take 16, value of t is your p into r, and pi d cube. D is your diameter of that. So d is your diameter. This is your diameter d, small d. And this is your radius. That this is your diameter d, and here's some radius of that helical axis. So this was your helical axis. So load was applied in this way. There was some r after that mean. We can call it as mean radius, and there was some diameter d here of this what you call as spring. So these are the details of that. 16 PR by pi d cube. And what the value of direct shear stress we can have? Do you know what value of shear stress that for the circular section? Maximum value we can have at a neutral axis, that is 4 by 3 P by area. That's 4 by 3. What's the value of shear force? That's P divided by pi d square by 4. Then we say that since your value is negligible, we say that 4 by 3, we can ignore that part. Then we write that tau d equals to 4p by pi d square. And if I write that equation in this, if I write those values in those tau max and tau minimum, I write 16t by pi d cube and plus 4p by pi d square. And in this one, I will write 16t by pi d cube, and it is in the opposite direction. I can write 16t by pi d cube minus 4p by pi d square. Then I kind of write it in terms of 16 by pi d cube, 16 by pi d cube. Yeah, 16 PR by pi d cube, 16 PR by pi d cube, 1 plus d by 4r. And in this one, I write 16 PR by pi d cube, 1 minus d by 4r. So generally, we then say generally that we write that d by 4r is very, very less as compared to 1. Then we write directly that tau max is equals to 16 PR by pi d cube. So this is the general value that's directly because of torsion because of tau t. And this part we can also keep that in mind, that we can have this part also because of direct shear stress. So this part is over. This part is over. Now we say that because you have spring, it can absorb energy. So it can absorb energy. What is the value of that strain energy stored in one spring we have? So you have some spring, and there might be n number of turns, each with a length of 2 pi r, each with a length of 2 pi capital R, each with a length of 2 pi r. Okay, so I would say total length of that L, total length of that spring would be some sort of, let's make that a total length of L dash, that would be n times 2 pi r. And there's some you're applying a torque that's equals to P times R. If you say what is the strain energy, do you know the equation for the strain energy in terms of torque? We have derived that equation, that what we call as T square L by 2 Gj, T square L by 2 Gj. If you have this one, so if you substitute those values, P square R square and n times 2 pi r capital R divided by 2g. What is the value of j we can have for if you have that diameter of the spring? If you have the diameter of that spring, so the j value would be equals to pi by 32, small d to the power 4, small d to the power 4. So if I write that, strain energy would be equals to 32 and 2 goes 32 p square r square n nr, yeah, p square r cube. We can write p square r cube n times divided by d to the power 4, and we have g also. Is this the equation? 32 p square r cube n by g to the power 4. So you got the strain energy. You want to say what is the deformation, actual deformation? What is the actual deformation of that spring? How can you calculate that actual deformation of the spring subject to the strain energy of U? So we say that by using Castigliano's second theorem, Castigliano's theorem, that dou U by dou P would be equals to, because you are applying load of P, so there will be some deformation, that's actual deformation. So I would say that that's equals to dou U by dou P. So if I substitute that, I would get a value of 64 P R cube N by GD power 4. Similarly, if you talk about that theta, you know that angle of twist, because you are applying torsion, angle of twist would get developed in that spring, that would be equals to TL by GJ. So value of T is equals to PR, L value is equals to 2 pi R N, and value of G pi D power 4 by 32. So this is your equation for that. And if you want to say what is the stiffness of that, what is the actual stiffness, what is the stiffness of this spring, K of that spring? So that's the load required, P required for unit deformation, P required for unit displacement. So that means if you substitute that value of P divided by value of delta, what is the value of delta? That is 64 P R cube N by GD4. 64 P R cube N by GD4. So finally you got that K value equals to P times PG, can I write that GD? Yeah, GD power 4 by 64 R cube N. So this is your equation. Now one thing is that from this one we can write that value of K into N is your constant function of GD power 4 by 64 R power 3. So this is a constant value for given diameter and for given that radius and given material G. So we say that this is constant. This is constant. K value, K into N. So stiffness into number of turners, that is a constant function. That's a constant value. So if I write that K1 N1 equals to K2 N2. Now one thing is that based on this we have a topic of what we call as change of stiffness of spring on cutting. Change of stiffness of spring on cutting. So there was some spring of n number of turners with the stiffness K. There was a spring of n number of turners with stiffness K. Then you say you cut it into two equal holes. You cut it equally. So you cut it equally into N1 and N1. That is N1 is equals to N by 2. N1 equals to N by 2. And there might be stiffness K1. Here also stiffness would be K1. And we don't know the value of K1. So I would say based on this equation we have Kn equals to constant. I can write K into N equals to K1 into N1. That is K1 N by 2. So I would say the stiffness developed for the the section which have only n by 2 number of turns, it would be having stiffness of twice the K. So I would say your K value increases, stiffness increases on decreasing those number of turners, on decreasing n number of turners. So now we can have the combination of those also. So we can have series arrangement of those, or we can have parallel combination also. W load for this bar, there's some W load and there's some stiffness K1, K2 series. So similarly K1, K2, K3, you applied a load of P, W downwards. So I would say for the series arrangement, we would say the total delta that has been developed is because of delta 1 plus delta 2 plus delta 3. Here we say total force in the springs Fs is same for all springs. F1 equals to F2 equals to F3. If you got the free, but if you have the free body diagram, you can show that also. You can have that in each of those springs we have same amount of force F. And in the parallel arrangement we say that the delta developed is equals to same. Delta is same, and that is force 1 plus force 2 is equals to total weight. And based on this one, that when you say that in the series combination, your delta is equals to summation of all those delta, and f is same, then you write an equation that what is the equivalent stiffness of that. What is the equivalent stiffness? Equivalent stiffness, that is summation of, that's reciprocals of those stiffness, 1 by 2, 1 by k3. So finally you got this equation. And if you talk about flexibilities, that is inverse of what you call as stiffness. So stiffness is that load required for unit deflection. Stiffness is load required for unit deflection. And flexibility is that what is the deflection developed for force of 1 kilonewton, for force of 1 unit. So flexibility is that. So flexibility is that if you calculate flexibility of equivalent flexibility, that is summation of all those flexibilities. And next one is that if you talk about parallel, we say the K equivalent equals to K1 plus K2 plus K3 and so on, so on, so on. And based on this now, we can take few problems. Before that, we have two definitions left. That's one is your proof load. Let's write that proof load. Proof load, that is maximum load that spring can take, maximum load carrying capacity of what you call as spring without getting distorted, without getting permanent distortion, without getting permanently distorted. So if you have that tau max which might cause permanent distortion, so there might be tau max which can be allowable. Tau max allowable, we can say allowed, which for the material. So tau max equals to 16 t by pi d cube, 16 t by pi d cube, 16 t by pi d cube. And based on this, we can get the value of P, that is equals to tau max times pi d cube by 16 R. So this is your proof load, we can say. This amount of load you can apply such that if the load is less than this P proof, so you can have the spring without getting permanently distorted. So based on this, let's take that what you call as problems. So let's try the first problem. Let's take the first problem that we call as, we have a helical spring that is alpha less than 10 degrees helical angle. We say that the helical angle is very small. It's mentioned that helical angle is small. That means it is giving hint that it is we are talking about closed helical coil, closed helical spring, that is alpha less than 10 degrees. Then so we got that it is talking about closed helical spring. Now it is subjected to pull of 1 kilonewton, and it's saying that it extends how much? It extends 10 millimeter for the load of 200 Newton. So for this load, it's extending this part. So it's a statement that's here. So we can get something from this statement. And the mean diameter of the coil is 80 millimeter. And you need to get the dia of the wire. You need to get the dia of that spring wire. So this is your d mean. That's we can say this is your d mean, capital D mean, and this is talking about that small d. And this next part is that you need to get the number of coils. Required. Or we can say number of turns. Number of coils or number of turns required. And for the given condition that G equals to 80 gigapascal and allowable shear stress is equals to 100 megapascal. So let's have that problem. Let's take that problem. So let's take the problem. If you talk about, so one statement is there, so we can get that stiffness of the, we can get the stiffness from the statement that K equals to P by delta. So for 200 Newton, we have 10 mm deflection. So 200 Newton, for 10 mm deflection. So we got that stiffness, that is 20 Newton per millimeter. And from the allowable shear stress, can we have the equation that if I write the allowable shear stress equation, that tau max tau allowable equals to 16 t by pi d cube. So I need that d, small d. I need that d, which is in this equation. So if I know other parts of this equation, so P is there. So we know that that P is there already mentioned, that pull of 1 kilonewton is there. That coil is having a pull of 1 kilonewton. If I write that 16 times 1 kilonewton into some that radius, mean radius, what it's provided at mean diameter of that coil is 80 millimeter. That means radius equals to 40 millimeter. You can write 40 millimeter divided by pi d cube, that is equals to 100 megapascal. And you can get the value of diameter. You can get the value of diameter, that is equals to 12.68 millimeter. This is the diameter of the spring wire. So you got this one. What is the next part it's mentioning? It's saying that you need to get the number of coils required. How can you get this part? Number of coils. Which equation is having that n part? One is your stiffness equation. Next one is your deflection equation. You can use any of these. So if I write that delta equals to 64 p r cube n by g d power 4. Similarly, you can take stiffness also, stiffness equation. Now, it's not giving any hint about that. What is the delta that we have to talk about, and what is the load we have? So we have two given loads. One is that on 200 Newton we have delta of 10 millimeter, and so we say that, so that's okay. If you have these two values, we can use them. But if you are using for 1 kilonewton, you don't know the value of delta. So if I use here 1 kilonewton, that means I have to use that delta corresponding to 1 kilonewton. But I don't know the value of delta corresponding to 1 kilonewton. That means I have to go with this data. If I use delta equals to 10 millimeter and P equals to 200 Newton, accordingly I can get, based on the same equation, I can get the values of that. So if I write that, I would say I would have used that equation of stiffness. Let's try that. I need the diameter, and I need the n. I need the value of n here. So I can write n is equals to gd power 4 delta by 64 r cube by p. So but I know that p by delta would be equals to k. So I can write gd power 4 by 64 r cube and k. I can get this value of k. So I know the value of k. I can use that part, 20 Newton per millimeter. So I can write that 20 Newton per millimeter. And you have this part also, g value of 80 gigapascal into diameter 4. The diameter we have 12.68 millimeter per 4. And we have that 64, and we have that mean radius of 40. Mean radius of 40 was there, mean coil diameter, and divided by 2. So we got this one, and accordingly we can get the number of turns almost equals to 26 turns. 26. Let's take that second problem. So we have a composite spring. So it has two closed coiled springs, two closed coils, or we can say closed coiled springs. That is, both have alpha less than 10 degrees, and they are attached in series. So there is one spring, and there is one more spring after that. So there we have two springs in series. One is having K1, K2. So accordingly we can have the other data also. So each is having, N1 is having equals to N2 equals to 12 number of coils, or we can say 12 number of turns. And we have mean diameter DM1 equals to DM2, that's equals to 25 millimeter. Both having mean coil diameter. This is mean coil diameter. So both have the same value of diameter of that what you call as axis about that helical axis. So there might be one spring might be in this fashion, and after that there is a one more spring of some smaller diameter. Let's say smaller diameter might be there, but that mean diameter is, how can you have the mean diameter same? How can we have the mean diameter same? So let's take that data as it is. So we have that mean diameter. Mean diameter is 25 millimeter. Mean diameter of both the wires is 25 millimeter. And if the mean diameter is both for those materials, that means we almost approximate that d. Actually, that mean diameter should be d plus some that thickness, that diameter by 2, small d by 2. One is your that spacing between those two, and plus d by 2. So, but we say that the thickness is very less, so we approximate it equals to 2r. So that's why he might be saying that if the thickness is, let's say, 2 millimeter, as from the data 2 millimeter, 3 millimeter, so we can ignore that. So we can take millimeter, dm almost equals to that value of 2r. So dm is 25 for both the coils, and it's giving that the diameter of the first wire is equals to 2.5 millimeter. You need to say what is the diameter for the second coil. Diameter of the wire of that diameter for the second wire. Diameter for the second wire, and it's giving that the K of the composite section, that's equivalent K equals to 700 Newton per meter, because you are in the series, so there is some K equivalent equals to, from this equation I can have that K equivalent equals to 1 by K1 plus 1 by K2. So this is also given that. Now you need to say what should be the maximum load, what should be the P max we can apply for this composite spring. See, if the springs are in series, that means the load that should be applied, it should be the minimum. It should be because for both the springs we should have same load. So if one is having if one can take lesser amount of load, we can take that value of P max here. And it's also mentioned that materials have the same value of G. G is also same, 80 gigapascal, and tau max is also same for the material. Tau max for both those springs we have same value of 180 megapascal. So what can you get from this data? So we have data is provided that we have n value given, d value is also given for 1, and k is given for equivalent, g is given for entire, tau is given. So this data I can have. If I have some equation in terms of this part, I might get something. So if it's mentioning that there's a composite K, that means I need to go for this equation. If it's talking about that equivalent K, so if I write that equivalent K of 700 Newton per meter, that is equals to 1 by K1 plus 1 by K2. Do we know the value of K? What is the equation for K? That's P by delta, and the value of delta PR cube. That's finally it becomes some sort of GD power 4 by 32 R cube N. In this fashion, some sort of equation becomes, for the stiffness, K equals to 64 R cube N by GD power 4. Yeah, GD power 4 by 64 R cube N. 64 should be here, 64. So this is our equation for the value of K. And if I have this one, so I know these values. That N, D, K, J, and I know these values here. I know that value G, D, R, and I know these values. I can have that in this equation. If I write that for the first case, the value of K1, what is the value of K1? That is G, but the D is different. See, from the data we can have that we say that the points which are the things which I am highlighting, that these are constant for both the springs. So G is constant for those both springs. For both springs, G is fixed. R is also fixed. That's your mean radius is fixed for both the materials because that is mentioned. Mean diameter is 25, that is r would be equals to 12.5 for both the materials. And value of n is also same, n1 equals to n2. So I can have that all these terms we can keep that outside, and we are only talking about that d to the power 4. So let's say that we have this equation now. Value of k1 would be equals to g d to the power 4 divided by 64 r cube n, and inside we have that d to the power 4 1 plus 1 by d to the power 4, similarly in this fashion. Okay, do you got it? Do you got this equation? Okay, let's take now the values of these. So we have unknown of d2, so this one is unknown, so accordingly we can get the equation now. We can write that. So I would say we have that 64 or r value of 25 by 2 cube, and multiply of n equals to 12 divided by the value of g equals to 80 gigapascal, and you have 1 by diameter 1 is 2.5 millimeter, 2.5 power 4 plus 1 by d2 to the power 4. So solving this part, so you can have then finally value of diameter 2 is equals to 2.109 millimeter. That is lesser than that 2.5 initial value. So then based on these values we can say the mean diameter is same for both the materials. So this is 2 millimeter. That means if you talk about that 2 millimeter, and if you talk about mean radius, if you talk about mean coil diameter, so there we have some spring. So it's having some thickness of what you call as diameter of 2 millimeter, and you go from this part to this part. So there might be some diameter. So this might be 2r, this might be 2r. So we say that actually we say mean diameter should have been up to the center line. Mean diameter should have been up to the center line. This one should have been our mean diameter, dm. But we say that dm equals to 2r, that's your internal dia. But because your thickness is very less, how can you add that small thickness of 2 millimeter here? So we say that mean diameter equals to 2r. Now the thing is what's that second part of that problem? We say you need to get the value of maximum load we can have for this composite action, for this composite spring, Pmax. For that Pmax, we need tau value, equation of tau. I know that proof load, it's talking about that proof load which we had. So it's saying that proof load, which one should be that proof load? I would take that proof load, that I have that equation of tau equals to 16t by pi d cube. So this t equals to pr. So accordingly I can get the value of p. So if I write that equation, that p equals to pi d cube tau by 16r, and based on these values I know that value of p is a function of d, because your tau is same for the two materials and r is also same. So I say p is directly proportional to diameter cube for this problem. So if I have that, I would write for the first material, how much is the proof load? I would say that is equals to pi times diameter of that wire. Diameter of that wire was equals to 2.5 millimeter, and shear stress value was, permissible shear stress was 100 megapascal, and divided by 16 times r. Value of r was 12.5 millimeter. So you have that value of p1. And similarly for the wire p2, we can have pi times diameter 2 we calculated. Diameter 2 was 2.109 millimeter cube. This is also cube, and you have 100 megapascal also there, tau max, and you have 16 times radius is also same. So you based on these two values we can say p1 equals to so since your function is p is a function of d cube, and smaller d value here is, we say diameter d1 is 2.5 and diameter d2 is 2.1. So minimum value would be corresponding to wire 2. So p minimum will be at the rate of wire 2. So that's equals to P2 is equals to 26.51 Newton. So this is your maximum load you can apply for this combination. Let's take the third problem. Let's take the third problem. So you have a truck. You have a truck, TRUCK truck. The truck weight is equals to 30 kilonewton weight. It has a weight of 30 kilonewton. And it's moving with a velocity of 6 kilometer per hour. And it has to stop. By using that buffer. So there we have buffer, and it has to stop. It has to stop because of that buffer. So we say that how many springs? So we have one spring. We have a spring, and number of coils for one spring equals to 20 coils. So I would say, and the spring goes compressed. Spring has to get compressed by amount of 200 millimeter. So there's some spring. You are applying a load. You are applying some energy in the form of kinetic energy of that truck, and it's getting compressed by some delta equals to 200 millimeter. So I would say kinetic energy is getting stored as in the form of strain energy in the spring. So for this mechanism, you say there we have one spring. How many number of springs we need? For this given amount of kinetic energy? How many number of springs we need? How many number of springs we need for this value of delta? So that those we can have those in parallel, we can say. So how many number of springs we need? So we got this problem, and other data that's provided to you, that's that mean coil diameter is equals to 200 millimeter, and diameter of that wire, spring wire itself, is equals to 20 millimeter. Value of G equals to 100 gigapascal. So if I say what is the kinetic energy that has developed for this one, I would say that's mv initial minus final whole initial square minus final square. So I would say mv square. So finally I would write 1/2 value of m, mass of that truck, would be equals to 30 kilonewton by value of G, that's 9.81 meter per second square, and multiply of V, velocity 6 kilometer per second. Then so accordingly you can get the value of that kinetic energy would be equals to 4248 Newton meter. If I say what is the strain energy developed, strain energy stored in one spring, how much strain energy has been stored? That is 1/2 of P into delta. So based on this data, do you know these values of P and delta? Do you know this value of P and delta? So I say that the value of that delta we know here. But value of P, how can we get this value of P? This is the concern. So if I have this equation of delta, if I say what's the value of delta for the spring, that's GD to the power 4 in this way, 64 P R cube and by GD to the power 4. And can I get this? At this delta, how much P is required? Can I get this value of P? And accordingly, I would say for this amount of delta, there might be some amount of strain energy stored that would be equals to 1/2 of P into delta, that P corresponding to that amount of delta on which you are talking about that strain energy. So we need to say what is this value of P. So I would say this value of P would be equals to the value of GD power 4 delta divided by 64 R cube. And if I have those values from this one, if I take those values, I can have the value of P. If I write that, what is the value of G? That's 100 gigapascal. And value of small d is equals to diameter of the wire, that is 20 millimeter. And delta, what is the delta we have? 200 millimeter. divided by 64, value of R cube, that's diameter, mean coil diameter divided by 2, that's 100 millimeter, 100 millimeter, 100 millimeter, and multiply of N. Each spring is having how much number of coils or turns? That's 20. So 20. So you can have that value of P is equals to 2500 Newton. And I can write that strain energy stored in one spring equals to 1 by 2 P into delta. So I can get the energy equals to, let's say, 250 Newton meter. So I would say this, I'm going to balance those. I would say that total kinetic energy is balanced by those strain energy stored in those springs. So I would say total kinetic energy was equals to 4248 Newton meter. 4248 Newton meter. That should be equals to in one, how much we have strain energy? 250 Newton meter. 250 Newton meter. So if I have X number of springs, we say X number of springs is equals to 17 springs we need for this mechanism. 17 springs. Let's take the fourth problem. So we have two closed coils. Springs. We can say springs. Closed coil springs. They are compressed. They got compressed by two parallel plates. By a load of 1 kilonewton. By 1 kilonewton load, you are applying a load of 1 kilonewton, and we have two springs. They got compressed by, because we have two plates attached. We had fixed them in between two plates. Then diameter of the wire, diameter of each wire, we can say that is 10 millimeter. Each wire is having diameter, each wire, spring wire, I would say. So D1 equals to D2 equals to 10 millimeter, and there is a mean diameter 1, there is a mean diameter 2. So that is equals to, first one is that 50 millimeter, 71, next one is that 75 millimeter. And we say that N1 equals to N2 equals to 10 number of coils. Each is having n number of coils, and we say that smaller diameter. We say that smaller one is placed inside the larger. So we have, because we have two different mean diameter of the coils. We say that we have two different mean diameter of the coils. So we say one is placed inside. So bigger, we can say smaller one, which is having smaller dia or mean dia. I would say smaller is placed inside bigger. So I would say there would be some, from this axis, helical axis, there would be some diameter that is equals to, there will be some diameter that is 37.5. There is some radius 37.5, and there is one more radius that is 25. There is one more radius that's 25. This part is 25. So one spring is placed inside the larger one, which is having bigger mean diameter of that coil. In this fashion we can have. So similarly, second one we can have inside that. In this fashion. So let's have those. We have attached those. Now these are subjected to that load of 1 kilonewton. Subjected to load of 1 kilonewton. So, and the problem says that delta compressed, that they have the same compression because they are attached parallel. In parallel, they are attached in parallel. We say delta is same for the both. It's given that delta is same, delta compression is same for the two. Wires, and you need to say what should be the value of their delta. Delta equals to delta 1 equals to delta 2. You need to calculate that value of delta. And next one is that you need to say what is the tau max 1 and what is the tau max 2. So what is the maximum shear stress that has developed in one material and second material. And corresponding to that G value, we have G value of 40 gigapascal. For both the materials, we have 40 gigapascal. So there is a 1 kilonewton load that's acting. So we have two plates. Let's say we have two plates, and you are applying a load of 1 kilonewton. So we say total load is shared between one spring and second spring. So since the combination is parallel, we say total load is having taken by the two springs. So I would say, and delta is same. We say delta is same for the two materials. Delta is same. And I would say I can get the relation between the two. If I say delta is same, I know the equation for delta. The value of delta equals to 64 p r cube n by g to the power 4. This is our equation for delta. And if we have two springs, for that 64 is constant. Value of p I don't know, so p would be p1, and r is also varying, so r1, and value of n is same, g is same, and diameter, we have that diameter of those two wires is same. Diameter of those two wires is also same, n is also same, and only that mean coil diameter is varying, g is also same. So I can have that equation. I would say this one is same, this one is n is also same, g is also same, d is also same. So I can write that p1 r1 cube equals to p2 r2 cube. Corresponding to this problem, we say this, we can have this relation. And if I say what should be the load 1, that is what should be that, we have two springs, spring 1 and spring 2. How much load p1 would take in terms of p2? That is equals to r2 cube divided by r1 cube, r2 cube by r1 cube, r2 cube by r1 cube. So we write 37.5 divided by 25. 37.5 divided by 25 power 3. So we get a value of p1 equals to some value of p2 times so we say that the p1 would be, we represented that p1 is corresponding to that smaller diameter coil. Okay, so this corresponding to this one we have p1, and corresponding to this one we have p2. Okay, you have to keep that in note. P1 is in terms of that diameter one, which is having 50 millimeter only. Okay, and which is having r1. Oh, okay, p1 and p2. So we got a value of p1 equals to that 37.5 divided by 25 power 3. Yeah, that's 3.3750 power into p2. So we got this equation that p1 is equals to p2 times 3.3750. So if I write that equation, that total load is shared between that two springs, p1 plus p2 equals to p1 plus p2. So I can write that 3.3750 p2 plus p2 equals to total load of, how much total load was applied? That was 1 kilonewton. So I can get that 1 kilonewton here. I can have that 1 kilonewton. So I can get the value of p2 equals to this plus 1 equals to this, and inverse of that into 100,000. So that's 228. So p2 is equals to 228.57 kilonewton, and p1 would be equals to 100 minus that, 1000 minus that. That is 771.42. So we got these. Let's keep that 43 Newton. So that means the load taken by the smaller spring is lesser as compared to that load taken by the bigger one. Actually, the diameter is same. We are saying that mean radius is different. So load 1 is more as compared to load 2, based on because we have that different mean coil diameter is. So because we have equation of that p is inverse of that r cube. So we say that because your p is inverse of that r cube, and p1 takes more load because it's having r smaller value of r. So accordingly we got the two values. And now the problem was saying you need to get the total delta. You need to get the value of total delta. So you can write any of these equations. We have delta, we can write delta equals to 64. You can write P1, value of P1 you can take 228.57, 228.57 Newton into R1 cube. That was your R1 was your 25. Corresponding to the P1, you have to take R1, 25 millimeter whole cube, and you have multiply of n. What is the value of n we have? Value of n was equals to 10 divided by g. The value of g was equals to 40 gigapascal, and multiply of d at d power 4. The diameter of the coil was itself equals to 10 millimeter. So we can get the delta 1 equals to delta 2 equals to delta equals to some delta equals to 154 millimeter. Now one more part of the problem was that you need to get the tau max1 and tau max2. We have that equation that 16pr cube by 16pr by pi d cube. So we say that for the tau max1 you can write p1, the value of r1, and diameter is same, so we can write diameter cube. Similarly, tau max2 we can write that is 16 times p2 r2 by pi d cube. So you use those values. You use those values that p1 was equals to 228 point. Actually, the value of p1 was not 228. The value of p1 was equals to 771.43. So we had to write here 771.43. The value of p1 was equals to 771.43. If you want to get from the delta 2, this was for the delta 1. If you want to calculate delta 2, that was 64 times 228.43. Then multiply of here we had to use 37.5 accordingly. So the delta 1 would be equals to delta 2. So you have to use here P1 equals to 771.43. 771.43. 771.43. So you can write that 771.43 and multiply of that R1 25 divided by pi, and diameter was your 10 millimeter, 10 cube. Accordingly, you can get tau 1, and similarly you can get tau 2 also. Some value of 5 into 57 into 37.5 divided by pi into 10 cube. So you can get the tau max1, tau max2. So one value is your 196.46. This one is your 87.3 megapascal. Let's take the final problem. Let's take the final problem we can have from these closed coilless springs. I would say you have a rigid bar. We call that as rigid bar, and we have three springs attached. One spring, second spring, and third spring. Let's have that K1, K2, K3. So I write that K1 equals to 30 kilonewton per meter, and K2, K3 equals to 18 and 12. And we say that before loading, length of those springs was same. L1 was equals to L2 equals to L3. That means beam before the loading, beam was horizontal. That rigid bar was horizontal. It's having some weight of self weight of 5 kilonewton, and it is subjected to load of 20 kilonewton also. There's some 20 kilonewton load is also acting on the bar at some value of x from the mid of that bar, and or we can say from the, because your K2 is at the mid. K2 is at the mid of bar. So you need to get the value of this x, where the load should be placed, where this 20 kilonewton load should be placed, such that final delta, or finally again, before the loading, L1 was L1, L2, L3 was same. That means beam was horizontal, bar was horizontal initially, and finally also we say bar should remain horizontal. If the bar should remain horizontal, for that condition you need to get the value of x. You need to get that value of that horizontal x. That means delta in all these three springs should be same. delta 1 should be equals to delta 2 should be equals to delta 3, because we are talking about parallel. And if you want to ensure that delta is same for the 3, delta is same such that your k1 gets compressed by some delta, and it also gets compressed by some delta, and it also gets compressed by same amount of delta, such that your final bar is also remaining that horizontal again as it was earlier. So we need to get that value of x from the mid of that bar or from the k2, so such that overall that what we call as overall rigid bar would remain horizontal. And we have the dimensions that the spacing between these two bars we have equals to that is equals to 0.4 meter, and this one is also 0.4 meter, 0.4 meter, 0.4 meter. And is any data needed? Is any data needed? I can say, based on this one, I can say this is a parallel configuration, and I would say delta would be same, because it's mentioning that delta should remain, bar should remain horizontal. That means delta should be same in the 3, because your bar is rigid. There is only 3 possibilities we know. One is this way, it can have horizontal there, or it can go in this way. So from the 3 possibilities, if the question is mentioning that we are talking about this one, that means delta 1 equals to delta 2 equals to delta 3. So if I have that, if I say what is the value of delta 1, delta 2, delta 3, I would say f equals to k delta. So I can write f1 by k1 equals to f2 by k2 equals to f3 by k3. That means out of that total load, so I would write total load of f1 plus f2 plus f3, that should be equals to 25 kilonewton. 25 kilonewton. If you cut that spring and show the free body diagram, I would say there we have some load of 20, then we have load of 5, and there we have some springs f1, f2, f3, f1, f2, f3, some forces of springs f1, f2, f3. Then I can write this equation. Now we got that, so we can get the relation now. I would say f1 by some stiffness k1, 30, 18, 12, 30, 18, 12, 30, 18, 12, 30, 18, 12, 30, 18, 12. So I can say f1 by f2, and there we have f3. So I can get that f2 is a function of f1, f2 is a function of f1, that is 0.18 by 30, that is your 0.6 f1, and f3 is your 12 by 30, that's 0.4 of f1. So I got that equation, and I can say that 0.6 f1 plus 0.4 f1 plus f1 is equals to 25 kilonewton. f1 plus f2 plus f3 is equals to 25 kilonewton, and I can get the value of f1. So force in the bar 1, that is equals to 12.5 kilonewton, and f2 is equals to 7.5 kilonewton, f3 value equals to 5 kilonewton. So that means if you make the line diagram now, so we say we have some bar, and you are applying a force of f1 equals to 12.5, and you are at the mid, you are applying a force of 7.5, and at the f3 location you are applying 5 kilonewton, 5 kilonewton, 5 kilonewton, and there we have some load of what we call as 20 kilonewton. I think 20 kilonewton was at a location of x from this point which is in the mid. So the distance here is 0.4. This is also 0.4, and I need to get that because there is some self weight also acting at that mid. Self weight is also 5 kilonewton. So if I say what should be the value of that x, can you get the value of x by the moment equilibrium? You can take summation of moments about any point. Let's say this point is O equals to 0. So if I say solve that, I would say 12.5, that's clockwise into length of 0.8, and one more load is 7.5, clockwise length of 0.4. Then we have anti-clockwise 20 kilonewton at a load distance of 0.4 plus x, and we have one more anti-clockwise 5 into 0.4, that should be equals to 0, and you can get the location of x equals to 150 millimeter or 0.15 meter. So x is equals to 150. So total was 400. That means at this location, this value is equals to 150 millimeter. And since your load is closer to this side, that's why reaction here is more as compared to the other side. So we got this one. So that's the end of that closed coils. So if you talk about a little bit about those leaf springs, if you talk about that leaf springs, we say they are the shock absorbers. They are the shock absorbers. Shock absorbers. We already saw where they can be used. They are also called as laminated or carriage springs. Laminated or carriage springs. Laminated springs or carriage springs. So the plates are attached in the form of leaves. We say that they are placed in the attached in the forms of leaves, and they are bent. Some sort of bent is there. In this fashion, they are attached. In this fashion. So there's some curvature already provided there. Already we have provided some curvature of that what we call as a leaf, or that is a plate of thickness t, and width is the same for all those leaves. We have thickness of that width of b and thickness of t, thickness of t. That's constant, but length is varying such that we have a beam such that it behaves as a beam of uniform strength. That means stress is same in all those plates. Sigma is same, it's uniform strength. L is adjusted such that length is adjusted between those such that sigma is same in all those plates. And there might be some because we have a bend that in the form of we have some sort of curvature. We say there is some deflection. You are applying a load of W. There is some curvature at the mid delta, and we say that that equation we have that we say it is behaving as a simply support beam. Here the reaction we have that W by 2, and in this side also we have reaction of W by 2. So we say that it is some sort of a beam subjected to point load at the midspan, and bending moment maximum would be equals to PL by 4, and that should be resisted by that section modulus into substress sigma z. And because we have n number of that plates, we write n times plates. So then we equate that total bending moment PL by 4 equals to that section modulus of BT squared by 6, and we have sigma also there. Sigma is constant, and we have n number of plates. Leaves, we can call them leaves. So based on that, we say that the sigma developed that sigma constant function value equals to 3 by 2 PL by n times BT square. So this is your sigma that has developed, and we can also get the delta. We can also get the value of delta deflection. That's based on that equation of external work done equals to internal work done. External work done equals to internal work done. So this is your equation for the external work done equals to internal work done, strain energy. So you solve that, and you get a value of delta equals to 3 by 8 PL cube by En BT cube. N is your number of plates. 3 by 8 PL cube by En BT cube. So this is the end of this chapter, what you call as springs. Thank you all for watching our series for strength of material. Thank you.